In this video, we discuss section 5.6, which is about inverse trigonometric functions and their derivatives. This is the sixth section in chapter 5, which is all about transcendental functions. So transcendental functions are logarithmic functions or exponential functions, all six trig functions, the inverse trig functions, and the hyperbolic functions. We covered these earlier this semester when we discussed units 1 through 4. So chapter 5, I almost think of it as a bonus chapter. We're just reviewing a lot of the concepts and techniques that we studied in chapters 1 through 4 or units 1 through 4, but now we're applying them specifically to our transcendental functions. It gives us a good opportunity to review those and to get comfortable with those and like a variety of problems. So that's the plan. We'll do this in this video, which is just sort of a trigonometric or trig review. And then we'll talk about the derivatives probably in the next video, maybe at the end of this one. And then we'll do some application problems. So we'll talk about approximating the function. We'll find relative extrema and do some curve sketching. We might do an implicit differentiation problem, and then we'll look at some applied problems. So real world applications and related rates can be, many related rates problems can be written in terms of inverse trig functions, and optimization. So just as a review, here's a graph of y equals sine of x. We know it has a period of 2 pi. It starts at 0, and then it follows this pattern. It goes from 0 to its max, then back to 0 to its min, and then back to 0. And all those interesting things happen. The zeros and the minimum and the maximum values, they all occur at 1/4 of the period, and the period is 2 pi. So this is one period of sine of x. And that repeats. So from 0 to 2 pi, you see one period, and then from 2 pi to 4 pi, you see another period, and then from 4 pi to 6 pi, you'd see the next period, and so on. It continues in that way. And then, of course, we can go backwards as well. From negative 2 pi to 0, we've got another period. And then negative 4 pi to negative 2 pi, we'd have another period, and so on. So looking at this, we know the domain of sine of x is all real numbers. So we can input any x value we want, and the output will be some number between -1 and 1. So we say that the range of sine of x is the interval from -1 to 1, because that's a set of y values that have x values. But this function, as it stands right now, does not have an inverse, because if I draw a horizontal line, and that horizontal line has an equation y equals c, where c is some number between -1 and 1, that horizontal line will cross the graph more than once. And remember what the horizontal line test says. It says if every horizontal line crosses the graph of f at most once, then f is 1 to 1. And if f is 1 to 1, then it has an inverse function. And we discussed that already. Another way that we can determine whether a function is 1 to 1 is to take its derivative. If its derivative is positive all the time or negative all the time for all x values in the domain. Then we know that the function has an inverse. But we can just visually see that sine of x, cosine of x, tangent of x, cosecant and secant and cotangent, all of those graphs or all of those functions do not have an inverse because they all fail the horizontal line test. And they all fail the horizontal line test because they repeat themselves, they're periodic. So we have to restrict ourselves to some interval in order to come up with an inverse function. Y is giving the sine of some angle. We might be interested in answering that question backwards. We might be interested in saying, okay, instead of saying if the sine of this angle is what value, you might say, I've got some value. What angle has this as its sine? So if we're interested in that question, we'd be looking for the inverse sine function or the arc sine function. This is y is the angle whose sine is x. And I actually tend to use theta here. So we'll say theta is arc sine of x. And that's going to be true if sine of theta equals x. Because if we take the sine of both sides, the sine of theta is going to be on the left-hand side, the sine of the arcsine of x is going to be x, provided that x is in the domain of the arcsine function and the theta is in the range of the arcsine function. So let's talk a little bit about domain and range. I said, okay, this function does not have an inverse as it stands, but if we restrict ourselves to some interval, it will have an inverse. Now, when we choose the interval that we're restricting ourselves to, we want to make sure that on that interval, we get all the y values from the original range. We want to make sure the restricted function maps onto the range. So every x value or every y value in this range has to have some x value on the interval of interest. And we want our function to be one-to-one. And we know from our previous studies of inverse functions, that means the function needs to be either increasing the whole time or decreasing the whole time, which means, in other words, that the function is strictly monotonic. So you just pick an interval where the function is either increasing for that entire interval or decreasing for that entire interval, and maps to that interval from -1 to 1. So we want all of those y values. Basically, this has already been done. A whole bunch of mathematicians, I guess, at some point got together and said, whenever we are using the inverse sine function or the arcsine function, we're always talking about this particular interval. So we're going to start at -π/2, and we're going to end at π/2, and we're going to restrict ourselves to this. If we restrict ourselves to this interval, we see that the function sine of x is increasing, and therefore it's 1-to-1. On this interval, every horizontal line crosses the graph at most once. There are some horizontal lines that don't cross the graph at all. Obviously, if y equals -2 doesn't cross the graph at all. But for all the y values between -1 and 1, if y equals some constant between -1 and 1, that horizontal line will only cross once. So it's 1-to-1. And if we choose the interval from -π/2 to π/2, then we get all the y values. At -π/2, the sign is -1, and at π/2, the sign is 1. And because the function is continuous, we get all of the y values in between as well. So what we do is we restrict ourselves to this interval, and then we switch the roles of x and y, and that is how we come up with this arcsine function. So let's graph the arcsine function. Now, if I just switched the roles of x and y, it's almost like drawing the sine function on its side. So almost like take my paper, draw it this way, and then instead of drawing the sine function going to the right, I draw my sine function going to the left. Now remember the sign, how the sign starts. We start at 0, and then we go up, and then we go down, or we start at 0, then we go up to the max, then back to 0, then down to the min, then back to 0, and then we go repeat that pattern. 0, max, 0, min, 0. 0, max, 0, min, 0, max, 0, min, 0, max, 0, min. That's how it repeats. Now, if I switch the roles of x and y, basically writing or drawing the relation x equals sine of y instead of y equals sine of x, I'm going to do the same thing, but I have to remember x and y are both positive in this quadrant right here. So I can't just draw the sine function over here, because then I'd be drawing it on the negative y-axis rather than the positive y-axis. So what we need to do is draw it this way. So I start at 0, and then π/2 later, it's going to be at its max of 1. And then π/2 later, it'll be at its min of 0. And then π/2 later, it'll be at its, or I said min, at a 0 at pi. And then π/2 later, it'll be at its min. And π/2 later after that, it'll be at its, back at 0. So it goes 0, max, 0, min, 0. But I've drawn it sideways. So we keep going like this. And you can draw that backwards as well. That graph is the graph of x equals sine of y. I'm going to call that an inverse relation. because it just comes from switching the roles of x and y. Obviously, it fails a vertical line test. It's not a function. And it fails the vertical line test because this original function failed the horizontal line test. But again, if we focus on this interval from negative pi over 2 to pi over 2, we will actually have a function, and we're going to call that the arc sine function. So we see that the original range of sine of x was -1 to 1. When we switch the roles of x and y, that range of -1 to 1 becomes the domain of arc sine of x. And that makes sense because we're switching the roles of x and y. So when we go from 0 to 1 to 0 to -1 to 0, we're doing the same thing here. We're going 0 to 1 to 0 to -1 to 0, but we've switched the roles of x and y. Now for the domain, we have to be careful. The domain of sine of x is supposed to be the range of the arc sine of x. But if we use the original domain, we're in trouble. It's not actually a function. So we have to take a restriction, or we have to use the domain of the restricted sine of x here. And the domain of the restricted sine of x was negative pi over 2 to pi over 2. So now the range of the restricted arc sine of x will be negative pi over 2 to pi over 2. So we're just interested in this part. When x equals -1, y equals negative pi over 2. Because negative pi over 2, -1 is on this graph. And on this graph, on the original graph of sine of x, when x equals pi over 2, y equals 1. Now on the graph of arc sine of x, when x equals 1, y equals pi over 2. All right, so that is the arc sine function. Now, when you're evaluating the arc sine function, you have to be careful about domain and range again. I lost the cap to that one. Let's say somebody asks you to find the arc sine of 1/2. Well, that's going to give me an angle. And that is the angle whose sine is 1/2. So sine of theta is equal to 1/2. You can think of it that way, or if you prefer, you can actually apply that sine function. You can say arc sine of 1/2 is equal to theta if we take the sine of both sides. Sine of arc sine of 1/2 equals sine of theta. And sine of the arc sine of 1/2 should be 1/2. And sine of theta is just a function. Now, sine of theta equals 1/2 has infinitely many answers. Because if I draw the horizontal line y equals 1/2 and say when is sine of x equal to 1/2, I'd get infinitely many solutions, right? So we have to be careful here. Arc sine only gives us one answer because it's a function. You put one x value in, 1/2, and you only get one theta value out, or one angle out. So you have to remember, if I'm saying arc sine of 1/2 equals theta, what's theta have to be? Well, I want the angle whose sine is theta, and I want theta to lie between negative pi over 2 and pi over 2. Because that was our restriction, because we chose to restrict ourselves to that interval from negative pi over 2 to pi over 2. So I say to myself, okay, just drawing some right triangles now. If my angle theta is between negative pi over 2 and pi over 2, that means I'm in quadrants 1 or 4. Sine is positive when y is positive, so we're going to be up here in quadrant 1. And sine, recall from trig, is opposite over hypotenuse. So it's the ratio of the length of the opposite side of the triangle. The side opposite theta is the one directly across from it in the triangle, divided by the length of the hypotenuse, which is the side opposite the 90-degree angle. There's a mnemonic. Sometimes I've seen a t-shirt for it. I really want this t-shirt. It says Camp SOHCAHTOA. Sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent, and then secant, cosecant, and cotangent can be thought of as reciprocals of those. But we want our opposite side to be 1 when our hypotenuse is 2. And we recognize that right away as a 1, 2 square root of 3 triangle. So the third side is square root of 3. And then the angle opposite the 1 in a 1, 2 square root of 3 triangle is the smallest angle. It's 30 degrees. So this is 30, 60, 90. This is 30, this is 60, and that's a 90-degree angle. So theta is 60 degrees. Oh, sorry, 30 degrees. But we want our answer in radians. 30 is 1/6 of pi. So I'll call that pi over 6. Or I'm thinking, what I'm really thinking to myself is 1/6 of 180. And then I remember that 180 is pi. So it's 1/6 of pi, which is pi over 6, or 1/6 of 180, which gives me the pi over 6. Okay, so if you see arcsine of 1/2 and you're asked to evaluate it, think it's the angle whose sine is 1/2, but I have to stick to this restriction. So it's not really that difficult, but you have to remember the restrictions for each of the inverse trig functions. Okay, so for sine, we restrict ourselves to negative pi over 2 to pi over 2. We've chosen an interval where the function is increasing that maps to that interval from -1 to 1 on the y values. So we switch the roles of x and y. The new domain is -1 to 1, and the new range is negative pi over 2 to pi over 2. But I'm not really thinking of this graph. I'm really thinking of this. I'm thinking, okay, I want arcsine is giving me answers, angles, who lie between negative pi over 2 and pi over 2. So if I draw my reference triangles, I'm drawing them in quadrants 1 or 4. That's how I tend to think. I don't tend to think about this. Although we can draw it just by thinking about drawing x equals sine of y and then just taking that part between y equals negative pi over 2 and y equals pi over 2. Okay, so that is the sine function and the arcsine function. The cosine function is similar, but instead of starting at 0 and going to its max, it starts at its max of 1. So its range is -1 to 1, its domain is all real numbers, and it repeats itself every 2 pi. We start at a max, and then we go to 0, then we go to the min, and then we go back to 0, and then we go to the max. And that repeats. All the interesting things happen at 1/4 of the period. The period is 2 pi. So half of that is pi, half of that is pi over 2. And then that pi plus pi over 2 is that 3 pi over 2 for the 3/4 of the period there. And this repeats itself. Of course, as this stands right now, it does not fail, or it fails the horizontal line test. It does not have an inverse because every horizontal line with the equation y equals c, where c is between -1 and 1, will cross that graph infinitely many times. And the function's only 1 to 1 if it crosses once. And we want it to be 1 to 1 again because we want, when we switch the roles of x and y, we want the resulting graph to be a function. We don't want it to be a relation. If the original function failed the horizontal line test, then when I switch the roles of x and y, the resulting graph fails the vertical line test, and so it's not a function. So we say, okay, we want to restrict ourselves to some interval so that the function actually has an inverse. Well, with cosine, the convention is to restrict ourselves to the interval from 0 to pi. So instead of going from negative pi over 2 to pi over 2 like we do with sine, we restrict ourselves to 0 to pi. So let's state that. We've got this restricted cosine function. So we're just looking at that one interval. We just happen to have chosen an interval where the function is decreasing. The domain of the restricted cosine function is 0 to pi. And the range is -1 to 1. We haven't changed the range at all. Whenever you come up with that restriction, you're always trying to choose your restriction so that it maps to the entire range. And this is, in this case, that interval from 0 to pi does map to that range of -1 to 1. So that's going to be a good choice for us when we switch to roles of x and y. Now switch to roles of x and y. And we can come up with the inverse function. This is y equals cosine of x. If I want x equals cosine of y, I'm just drawing that cosine function on its side. So I almost turn my paper sideways and start drawing a cosine curve. I start at the max, then I go to 0, then I go to the min, then I go back to 0, then I go back to the max after that. So it's max, 0, min, 0, max. And then that pattern repeats down here as well. But again, that is not a relation, or that is a relation. It's not a function. We're only interested in the part that corresponds to this part of the cosine graph. So since the range of the cosine function was -1 to 1, the domain of the arc cosine function, it's the range of the cosine function because we're switching the roles of x and y, is -1 to 1. So we're on the interval from -1 to 1. Then we said, okay, when x equals 0, y equals 1. So when x equals 1, y equals 0. When x equals pi over 2, y equals 0. So when x equals 0, y will equal pi over 2. And when x equals pi, y equals -1. So when x equals -1, y will equal pi. And so we just get this part of the cosine graph. And again, it's just switching the roles of x and y, it's turning that cosine function on its side. It's like, I really do think about just drawing it sideways and then reflecting it. Normally you just draw it, you turn your paper like this and then draw it as usual. But instead of drawing it with the positive x-axis this way and the, or the not positive x-axis, with the independent variables positive axis this way and the dependent variables positive axis this way, we have to remember that our dependent and independent variable are both positive in this quadrant instead. So that's why you have to do the reflection, the left-right reflection whenever you graph it. But because it's cosine, you don't have to do that. When you do the left-right reflection, it looks exactly the same. So this is our arc cosine function, this orange function here. So this is equivalent to the following. If I take the cosine of both sides, cosine of y equals x, and y is an angle. Y is between 0 and pi. I know I had theta there on the other one. I actually prefer to use theta. So the domain of the arc cosine graph is the range of the cosine graph, which was -1 to 1. And the range of the arc cosine graph is the domain of that restricted cosine graph. And it's mathematical convention to take the restriction for cosine of 0 to pi. So that's our function. Now let's say somebody asks you for the arc cosine of negative square root of 3 over 2. Well, I always think to myself, okay, that's an angle. And that is the angle whose cosine is negative square root of 3 over 2. And remember, with your arc cosine function, you're always getting an angle between 0 and pi. So I say to myself, okay, where's my cosine negative? Quadrant 1 or quadrant 2? Because if my angle is between 0 and pi, my reference triangle is either going to be in quadrant 1 or quadrant 2. Cosine is positive when x is positive and negative when x is negative. So we'll have a triangle over here. The adjacent side is square root of 3. When the hypotenuse is 2, because cosine is adjacent over hypotenuse. Remember again, so ka toa. Cosine is adjacent over hypotenuse. So when the adjacent side is negative square root of 3, the hypotenuse is 2. And we recognize that as a 1, 2 square root of 3 triangle. So that reference angle is a 30-degree angle again. Sorry about the coincidence there. That means our angle, theta, is 150 degrees. And again, I think in terms of degrees, and then I always convert to radians. So theta is 150 degrees, or that's pi minus 30 degrees, or pi over 6. So it's going to be 5 pi over 6. And again, I'm thinking pi is 180. I'm subtracting a sixth of 180. So how many sixths of 180 am I left with? 5 sixths of them. Because it's 1 minus 1/6 is 5/6. So that's what we have for our theta value there. Now, it might be tempting to say that that angle is 100 or 210 degrees. You might say, well, why isn't it this one over here? Why can't I draw my reference triangle in quadrant 3? Well, the reason we can't do that is because we want our theta to lie between 0 and pi. Now, if somebody just asked me, what are the solutions of cosine of theta equals negative square root of 3 divided by 2? There would be infinitely many solutions. I would graph y equals negative square root of 3 divided by 2. I would find 2 solutions, one in quadrant 2 and one in quadrant 3. And then I would add 2 pi n to those where n is an integer. We'd have infinitely many. But remember, arc cosine only gives you one answer because it's a function. And because of our choice of restriction, because of this mathematical convention, it's always going to give us an angle between 0 and pi. So that means it's always going to give us an angle in quadrants 1 or 2. Tangent is similar. Now remember, tangent is sine divided by cosine. So the tangent function has asymptotes whenever cosine of x is equal to 0. And we know cosine of x is equal to 0, it'd all be odd multiples of pi over 2. So at x equals negative pi over 2, at x equals positive pi over 2, at x equals 3 pi over 2, and so on. Our tangent will be undefined, and it's increasing. It looks like this. And it repeats every pi radians. All right, so that is our tangent function. Again, it fails the horizontal line test for the same reason that sine and cosine do. So we say, okay, if I want an inverse function, I cannot take the entire tangent function. I can only take part of it. Which part will we take? Well, the convention is to take this middle branch. So we restrict ourselves to the interval from negative pi over 2 to pi over 2. So the domain of the restricted tangent function is negative pi over 2 to pi over 2. The range of tangent of x in general is all real numbers. Excuse me. Notice that we chose a branch of the tangent function that would give us all real numbers. We wanted to make sure we mapped to that entire range, and we do. So now we switch the roles of x and y. Since the particular branch we're interested in had vertical asymptotes at negative pi over 2 and pi over 2, when we switch the roles of x and y, the arctangent function has horizontal asymptotes at y equals negative pi over 2 and y equals pi over 2. And it looks like this. This is y equals arctan of x, and that is equivalent to the following statement. If y equals arctan of x, then tangent of y equals x, and y lies between negative pi over 2 and pi over 2. So when I'm evaluating an arctangent, I'm always thinking about being in quadrants 1 or 4. If my arctangent, or if I have a negative number here, or excuse me, if I have a negative number here for x, then I want my tangent value to be negative. Tangent is negative in quadrant 3, or excuse me, in quadrant 4, and tangent is positive in quadrant 1. So based on whether that x is negative or positive, I know which quadrant I'm in, and then I can draw my reference triangle and finish the problem. So here's an example. Let's say someone tells you to find the arctangent of, goodness. Let's just say -1 divided by square root of 3. Say, okay, well, that's an angle. The tangent of that angle is -1 divided by square root of 3. And the angle is between negative pi over 2 and pi over 2. So where's my tangent negative? And out of quadrants 1 and 2, excuse me, 1 and 4. So we're looking for angles between negative pi over 2 and pi over 2, right? My tangent is going to be negative down here. Tangent is opposite over adjacent. So the adjacent side is square root of 3 units when the opposite side is 1 unit. And since y is negative in that quadrant, we have a -1 there. It's another 30-degree reference angle. I kept coming up with those 30-degree reference angles. That's a 1, 2 square root of 3 triangle, which means it's a 30, 60, 90 triangle. That means our reference angle is 30 degrees. But this arctangent is going to give me an angle between negative pi over 2 and pi over 2. So it's going to give me a negative angle in quadrant 4. So theta is actually negative 30 degrees or negative pi over 6 radians. Oops. Sorry, I keep drawing the same triangle with the same reference angle. Just sort of guessing. It's coming up with these problems off the top of my head, and I guess I kept accidentally choosing the same triangle. All right. So that's our tangent. So notice, arctangent always gives us angles in quadrants 1 or 4. Arcsine also gives us angles between in quadrants 1 and 4. And arccosine always gives us angles in 1 and 2. And that's because we chose this restriction from 0 to pi to start. Okay, so those are our first 3 trig functions and their inverses. Now we might be interested in secant. Now, to graph secant, I always start by graphing the cosine function. Because the secant of x is 1 divided by cosine of x. So I use the cosine of x as my guide to graphing the secant graph, graphing the secant function. Now cosine starts at 1, and again, we've talked about this before. Starts at 1, then it's 0, then it's -1, then it's 0, then it goes back to +1. And that happens every 2 pi radians. And then it repeats. 0, -1, 0, +1. Zero, -1, 0, +1. But secant is 1 divided by that, so we can't divide by 0. So secant is going to have asymptotes every time cosine is 0. Vertical asymptotes, so at all the odd multiples of pi over 2. And I'm going to graph my secant function in blue. Now when cosine is 1, secant is 1 divided by 1, so it's 1. When cosine is -1, secant is 1 divided by -1, so it's -1. So at all the minimum and maximum values on that cosine graph, those are also points on the graph of the secant function. And then as we approach those asymptotes, we have to think about taking 1 and dividing it by the y values in the cosine graph. So I'm dividing by a tiny positive number here and here. 1 divided by a tiny positive number is a large positive number. So it looks like that. And then similarly, as we approach negative pi or positive pi over 2 and positive 3 pi over 2 here from the right and left respectively, I've got 1 divided by a tiny negative number here and here. 1 divided by a tiny negative number is a large negative number. So the function goes to -infinity as it approaches those asymptotes from those sides. And then that pattern repeats. So secant's got these sort of weird U shapes. And that's what the secant graph looks like. A couple things I want you to notice. The domain of secant is all real numbers except the odd multiples of pi over 2. Because that's when cosine is 0. And then the range has 2 pieces. The range goes from -infinity all the way up to -1, and then it skips all the y values between -1 and 1. Because secant is 1 divided by cosine. Dividing by that fraction between -1 and 1 gives us a number that's larger than 1 every time, larger than 1 in magnitude. So we end up with all the y values from -infinity to -1. We skip all of these, and then we start again from going from 1 to infinity. So our range is this. And then again, just like before, we ask ourselves, do we have an inverse? Does this function have an inverse? And we say no, because if I draw a horizontal line with y equal, where y is equal to a constant, and that constant value is either greater than 1, greater than or equal to 1, or greater than or less than or equal to -1, that horizontal line will cross the graph infinitely many times. And we say, okay, I don't want to cross the graph infinitely many times. I want to choose part of the secant graph so that the horizontal line only crosses once. Well, you say, well, what is the mathematical convention? Which intervals do we choose? Well, because secant is 1 over cosine, and because we chose the interval from 0 to pi for cosine of x, it makes sense to choose the interval from 0 to pi for secant of x as well. So we're going to look at this part of the secant graph and this part of the secant graph. Now we still have that range. We go from -infinity to -1 and then 1 to infinity. So we're still mapping onto the range. And that's it. Our our domain of that restriction is 0 to pi. We start at x equals 0, and we go to x equals pi. Then we have to rule out that x equals negative pi or x equals positive pi over 2 because we've got a vertical asymptote there. So with our restricted secant function, the domain is, I wanted to write restricted secant, but it just doesn't look right in those parentheses, does it? Is 0 to pi, excluding pi over 2. So we go from 0 to pi over 2, and then we go from pi over 2 to pi. And then the range is the same range as before. So we went from, negative infinity to negative 1. And then we skip all the values from negative 1 to 1. And then we go from 1 to infinity. Okay. So now you switch the rules of x and y. So I probably should have left myself more space. Now this graph has a vertical asymptote x equals pi over 2. So when we switch the rules of x and y, our graph will have a horizontal asymptote y equals pi over 2. And on this graph, when x equals 0, y equals 1. On our graph, when x equals 1, y will equal 0. And then on this graph, when x equals pi, y equals negative 1. On this graph, when x equals negative 1, y should equal pi. So we have that point. You say, okay, well, what about this limiting behavior? See, on the original secant graph, what happened? As x approaches pi over 2 from the left, the y values go to infinity. And as x approaches pi over 2 from the right, the y values go to negative infinity on that secant graph. Now, when you switch the rules of x and y, we'll have as x goes to positive infinity, y will approach pi over 2. And since that's a negative there, we're approaching pi over 2 from below. So our function is getting very close to pi over 2, but it's never exceeding it like that. So I'm going to put a little negative sign there, but usually when we're talking about the function value, we don't really talk about approaching from the left or the right. Although we can think about it in pretty much the same way that we think about approaching x from values that are slightly larger or slightly smaller. We're approaching pi over 2 from values that are slightly smaller. Now, switching the rules of x and y here, as x goes to negative infinity, y approaches pi over 2 from above. I'm putting that in parentheses because that's sort of my notation, and I've never seen it anywhere else. I wouldn't expect to see that in another textbook. So we're approaching pi over 2 from above. So it's going to look roughly like that. And that is the arcsecant function. Now, when it comes to evaluating this, it's a little bit tricky. Let's say somebody asks you for the arcsecant of something. It's just like before, if somebody says that y equals the arcsecant of x, so they're giving you an angle. Y is an angle. It is the angle whose secant is x. Now, I don't think in terms of secant, I think in terms of sine, cosine, and tangent. So I say, I need to state my restriction on y. But my y value also has to be between 0 and pi. And of course, y is not equal to that pi over 2 because that's not in the range of the arcsecant function. But going back to this statement, like I don't think in terms of secant, I think in terms of cosine. So I always rewrite that as cosine of y equals 1 divided by x. So taking the reciprocal of the left-hand side and taking the reciprocal of the right-hand side, I get that. So we want cosine of y equals 1 over x, and y is between 0 and pi. Y is not equal to pi over 2. Sometimes I will actually answer this question. Try to figure out the angle whose cosine is 1 over x and gives us an angle in quadrants 1 or 2. That's the way I think about it. It's the way I have a tendency to think about it. And actually, y can be 0 or pi because we've got those function values. The function arcsecant is well defined at -1 and 1. Okay, so with that in mind, let's say someone asks you to find the arcsecant of, let's say, negative square root of 2. Let's say that's an angle. That is the angle whose secant is negative square root of 2. And say, I don't really think that way. I think in terms of cosine, so I take the reciprocal of both sides. This is negative 1 divided by the square root of 2 as our cosine function. And they say, well, where is cosine negative? It's negative in quadrant 3. This is -1 when this side is 2. So that's a 1 square root of 2 triangle. So we know our reference angle is 45 degrees. And this is our actual angle theta. So theta is 180 minus that 45. So is that 135? But I'm also thinking, okay, if that's 45 degrees is pi over 4. This is pi minus pi over 4. So this is going to be 3 pi over 4 in radians. Now, one thing that our calculators don't have is an arcsecant button, an arc cosecant button, or an arc cotangent button. We've got inverse tan, inverse sine, and inverse cosine, and they use that inverse notation. Instead of writing arc sine of x, they have a tendency to write sine to the -1 of x to mean the same thing. I don't like to use this notation because it reminds me of cosecant, reminds me of 1 divided by sine. So I won't use this, but this is what your button has a tendency to look like on your calculator. Since our calculators don't have this button, we have to do something else. Well, in that case, whenever I'm computing the arcsecant using a calculator, I would use the arc cosine button and take the reciprocal of whatever is inside. So if I needed to do this on a calculator, I could say, well, what is the arcsecant of a negative square root of 2? Well, it's the same as the arc cosine of -1 divided by square root of 2. And then with that in mind, I'll get the right angle. It'll give me that angle between 0 and pi that gives me the appropriate cosine value and then the appropriate secant value as well. All right. 2 more inverse trig functions. We had just did secant. Let's do cosecant. Cosecant is 1 divided by sine of x. Sine looks like that and it repeats. Now, cosecant is undefined whenever sine is 0. So cosecant is undefined at all of the multiples of pi, because sine is 0 at all the multiples of pi. Sine has a minimum of -1 and a maximum of 1. And very similar to the secant graph, when sine is 1, cosecant is 1. Because 1 divided by 1 is 1. When sine is -1, cosecant is -1 because 1 divided by -1 is -1. So we had these little points, the minimum and maximum, those locations of the minimum and maximum values of sine of x are on the graph of cosecant of x. And then as we approach either of these lines, or these vertical lines, we're taking 1 and we're dividing by a tiny positive number here and here. So the limit of the function is positive infinity. And then 1 divided by a tiny negative number there and there gives us negative infinity as our limits there. And that pattern repeats. So this is our function, the cosecant function. And again, we take a restriction of the cosecant to make it invertible in order to find an arc cosecant. And that's relatively simple, relatively easy to do. Because we choose the interval from 0 to pi over, or negative pi over 2 to pi over 2 for the restriction for sine, in order to compute that inverse sine, we use the same interval for the cosecant function. So, and it's not just because of the calculator thing, but that's part of it. If I restrict myself to the interval from negative pi over 2 to pi over 2, you can see the range is still negative infinity to negative 1 and 1 to infinity, that union. The domain is this interval from negative pi over 2 to pi over 2, but we exclude x equals 0 because we can't divide by 0. And then we switch the roles of x and y. The domain of the restricted cosecant function is negative pi over 2 to 0, union 0 to pi over 2. And the range of that cosecant is still negative pi over, or negative infinity to negative 1, union 1 to infinity. Then switch the roles of x and y to come up with that cosecant graph. We see we've got a vertical asymptote at x equals 0. Now we'll have a horizontal asymptote at y equals 0. When x equals pi over 2, y equals 1. So when x equals 1, y will equal pi over 2. Here, when x equals negative pi over 2, y equals negative 1. So when x equals negative 1, y will equal negative pi over 2. And then that limiting behavior. For me, it's helpful to write it out. As x approaches 0 from the right, the y values go to infinity. And as x approaches 0 from the left, the y values go to negative infinity. So here, when we switch the roles of x and y, as x goes to positive infinity, y should approach 0. And I'm going to put that in parentheses from above. And as x goes to negative infinity, y should approach 0. But here we're approaching from below. And again, it's not convention to use this with our dependent variable, but we can still think of it that way. So as we go to positive infinity, we approach 0 from above. As x goes to negative infinity, we approach 0 from below. And that is the arc cosecant graph. And of course, the domain of the arc cosecant is the range of the arcs, or of the cosecant. because we switched the roles of x and y. And the restricted domain of cosecant is the range of arc cosecant. All right. So that is that. We did the arc secant, the arc cosecant, we did the arc tangent. I think the only one left is arc cotangent. And I didn't talk about evaluating this, but again, it's very similar to what we talked about before. Y equals arc cosecant of x if and only if the cosecant of y equals x and y is in a particular range of values. So y is between -pi/2 and pi/2, and y is not equal to 0 because y equals 0 is not in the range of that function. But again, I don't really think in terms of cosecant, I think in terms of sine. So I think, okay, well, when is sine of y equal to 1 over x? And I still need that restriction on my y values. Now, if I want this, and I don't know if this is not the sine value for a special angle, and I need to use a calculator, I would use the inverse sine of 1 over x here. So the arc cosecant of x is equal to the arc sine of 1 over x. And I use that whenever I have to use my calculator to evaluate that function, because my calculator has an inverse sine function, and it has an inverse cosine and an inverse tangent function, but it doesn't have an arc cosecant or arc secant or arc cotangent. But we can find those in terms of these because we choose the same restriction of the cosecant function that we choose for the sine function. And because we choose the same restriction of the secant function that we choose for the cosine function because of that relationship. And the same is true for tangent. Tangent, we chose this interval from -pi/2 to pi/2. Ooh, I wonder, with cotangent, do we choose the same restriction? I don't think we do. I bet we use 0 to pi for cotangent, but I'm not 100% sure. I bet it's 0 to pi. I need to check the book and make sure. But let's look at cotangent real quick. So cotangent looks like this. Cotangent is cosine of x divided by sine of x. So it has asymptotes whenever sine is 0, and sine is 0 at all the multiples of pi. Now, where tangent increases on its entire domain, cotangent always decreases. So it looks like this. And it repeats. Obviously, this does not pass the horizontal line test. It does not have an inverse as it stands. We say, okay, well, what can we restrict ourselves to? I think it would make the most sense to restrict ourselves to the interval from 0 to pi. I bet it's 0 to pi. Let me look that up real quick. Okay, so that's what we have. We are going to restrict ourselves to 0 to pi. Now you have to be careful with this one if you're using a calculator, and we'll talk about that in a minute. But we'll restrict ourselves to 0 to pi. The range of the cotangent is still negative infinity to infinity. And then we switch the roles of x and y. So the range of the cotangent will become the domain of the arc cotangent. So our domain will be negative infinity to infinity. And then the domain of the restricted cotangent will become our range. So our range will be 0 to pi. And we see that x equals 0 and x equals pi are vertical asymptotes of that graph. So y equals 0 and y equals pi will be horizontal asymptotes of this one. And then at x equals pi, our cotangent is 0. I wrote pi, that should be pi divided by 2, sorry. Because pi over 2 is 0 here, or x equals pi over 2 corresponds to y equals 0. When we switch the roles of x and y, when x equals 0, y will equal pi over 2. And then here, as x approaches 0 from the right, y goes to positive infinity. And as x approaches pi from the left, y goes to negative infinity. So when we switch the roles of x and y, as x goes to positive infinity, y will approach 0. And as x goes to negative infinity, y will approach pi. And since we were approaching 0 from the right here, this is going to approach 0 from above. And since we were approaching pi from the left here, this will approach pi from below. So what we have is this. Approach 0 from above. And approach pi from below. And that's the arc cotangent graph. Now, if you have arc cotangent of x, or arc cotangent of 1, and you're just wanting to evaluate that, well, you've got some options. You say, well, that's theta. And what theta angle is that? It's the angle whose cotangent is 1. And we know cotangent is adjacent over opposite. It's a reciprocal of tangent. So you say, okay, well, when is cotangent positive? Well, it's going to be positive between quadrants 1 and 2. It's going to be positive in quadrant 1. And we know that that angle is a 45-degree angle. So theta equals 45 degrees, or pi over 4 radians. Now you might think in terms of tangent instead. So it might look a little different if it was tangent instead of that. How about this? Let's say somebody gives you the arc cotangent of, let's say 3/5. No, that's 3/4. Actually, let's use a negative value. Let's say negative 3/4. Well, that is an angle. We'll say that's the angle whose cotangent is negative 3/4. Okay, and we do need to add that restriction. And that angle is between 0 and pi. Now, if I draw my reference triangle, excuse me, we know cotangent is adjacent over opposite. I still don't think that way. I still think in terms of tangent. Tangent is opposite over adjacent. So I'll take the reciprocal of both sides. So what this tells me is that when my adjacent or when my opposite side is 4, my adjacent side is 3. And since we are in quadrant 2, my x value is negative and my y value is positive. We know 3 squared plus 4 squared is 5 squared, is 9 plus 16 is 25. So the hypotenuse is 5. And we want to know not what this angle is, that's our reference angle. We want to know what that angle is. So we're trying to find that value of theta. I say, I don't know what that is. I'd like to use a calculator. My calculator doesn't have a cotangent button. What am I going to do? Well, we need to find the reference angle for this. In order to find the reference angle, I'm going to use my calculator. And we'll use the calculator to compute arctangent of 3 or negative 4 divided by 3. Now be careful. Arctangent always returns angles in quadrants 1 or 4. So if the tangent is negative 4 divided by 3, this is negative 4, that's 3, and we still have that 3, 4, 5 triangle. It's going to give me an angle, but it's going to give me that negative angle. I don't want that negative angle. What I want is that negative angle plus pi. I want this one over here. I'm not interested in that angle. I want that angle from there to there. So we use our calculator to compute this, and then add pi to get the arc cotangent of negative 3/4. I hope that makes sense. The reason we do that is because we don't have an arc cotangent button on our calculator. But we do usually have a tan inverse. It looks like tan to the -1. I don't like that notation because it looks like it might be cotangent. So I always like to specify that it's an arc tangent to remind myself that it's an angle. Arc sort of stands for angle for me. So I see that arc tangent and I know I'm getting an angle back. We say, okay, my arc tangent is negative in this quadrant. Is my arc cotangent well defined there? Does my arc cotangent give me angles in quadrant 4? Never. Arc cotangent always gives me angles in quadrants 1 or 2. So you have to remember in this case to add pi to it. Now, if this was a positive 4/3, or if this was a positive 3/4, then the cotangent would be positive in quadrant 1, and the corresponding tangent function would be positive in quadrant 1. So you could just use your inverse tangent function, and it would give you the right answer the first time. It's only when we are in the wrong quadrant that we have to add pi. And I don't even try to memorize a hard and fast rule. What I do is I try to remember my 6 trig functions and their restrictions, the restrictions on their domains the restrictions on the domains of the original trig functions that allowed us to define the inverse trig functions. And then say, okay, what angle will I get out of this? Is that angle in the right quadrant? And if the angle is in the wrong quadrant, then add pi or subtract pi or do whatever is necessary to get into the correct quadrant. So that's what I would do for a problem like that. Okay, this has been a long video. I think we'll stop. We've covered all 6 inverse trig functions. We know what their graphs look like. We know how to evaluate those functions. In the next video, we can talk a little bit more about the derivatives. I think we've already covered all of the derivatives of those functions, but we will apply those derivative rules to some new application problems in this set of videos about section 5.6. But one more thing before we go, I wanted to show you that Desmos actually does allow us to evaluate the arc cotangent function. I think it allows us to evaluate the arc cosecant and arc secant functions as well. But if you're using one of those scientific calculators that you're typically allowed to use on exams, the scientific calculators like a TI, I forget what the TI model is. It's like a $10 or $20 calculator. But students are allowed to use them on exams. Those are the ones that only have this inverse sine, inverse cosine, and inverse tangent buttons. But Desmos, our graphing calculator online, has no problem with arc cotangent. So I asked it to compute arc cotangent of -3/4. It gave me this angle of 2.21 radians. I think I want to multiply by 180 and then divide by pi. So that's 126 degrees. That sounds about right. That looks about right to me. The reference angle is pi minus that. Or whoops, not pi minus that. Let's do 180 minus that. So the reference angle is 53 degrees. That makes sense with a 3, 4, 5 triangle. The opposite, the side with a 4, opposite the 4, the angle would be 53 degrees. The opposite the 3, it's going to be 90 minus 53, or about 37 degrees, right? And then opposite the 5 is that 90-degree angle. But yeah, this Desmos will give you the value of the arc cotangent button. But I did want you to see that if you compute the arc tangent of the reciprocal and then add pi, you get the same answer. So if I just used my calculator, my regular scientific calculator to compute arc tangent, it would give me that angle of negative 0.927. Or if I convert to degrees, that's negative 53 degrees. And I say, that's not the angle that I'm looking for. I'm looking for this other angle in quadrant 2 rather than the one in quadrant 4. So then we would just add a 180 to that. And we get the 126. But the exact answer in radians is this answer here. 2.21 radians approximately.